Let's look at LeChatelier's principle for stresses that involve changing an equilibrium by altering the temperature. So as a reminder, LeChatelier's principle says that if a chemical system is at equilibrium and it experiences a change, then the equilibrium will shift to partially counteract this change. That is, the new equilibrium that is established will have shifted towards the reactants or the products to partially undo the change you've imposed. What does that mean for a temperature dependence? So we think about a temperature change. One way to think about this problem is to imagine that the heat of the reaction is either a reactant or a product. For example, the formation of ammonia, nitrogen plus hydrogen makes ammonia, is an exothermic reaction. And as a result, if you run the reaction at constant temperature, heat is released, and we can think of heat as one of the products. So if we increase the temperature, then to increase the temperature we have to somehow input energy in the form of heat, and that's like adding a product. And thus the reaction would shift back to the reactants to partially compensate this. That is, the new equilibrium would be established and we would have more reactants than we did at the other temperature. Now this isn't exactly the way we should think about it because we're not actually adding any products, and previously when we changed concentrations the effect was that we were shifting to a new equilibrium because the mass action expression Q was no longer equal to the value that it had at a particular temperature K. What is changing here? The thing that's changing here is the equilibrium constant itself. And so the equilibrium constant is constant unless you change the temperature. That is, the concentrations or the partial pressures will always adjust until they achieve the lowest free energy value, which is the value they can have at equilibrium. But now, as we change the temperature, it's that equilibrium constant that's changing. K is a function of temperature. Why is that? Let's look at our understanding of K from a free energy perspective. So delta G is equal to minus RT natural log K. And so we can imagine delta G has a temperature dependence, and there's another temperature in the equation. And so when we're looking at this, you always want to realize that the temperature dependence of K has several factors. So we can break that down by isolating K. So if we look now, rearranging this equation, we have delta G, its temperature dependence, it's delta H minus T delta S. Now for this example, we're going to simply assume delta H and delta S are independent of temperature. And that's a little approximation. They have a temperature dependence as well, but that's another subtlety. And here we'll just say the big temperature dependence comes from the fact that the entropy term is multiplied by the temperature. Now, isolating this and putting in the natural log K part, we see minus RT natural log K, and now I've put K in parentheses there as a function of temperature because that's what we want to think. What is the temperature dependence of K? That's equal to delta G, which is equal to delta H minus T delta S. And now isolating the part we care about, the natural log of K is now minus delta H over RT plus delta S over R, and you can see the temperature that used to be multiplied by the entropy term has gone away because we divided both sides of the equation by minus RT. So that has a particular consequence when we look at this. That is, if we say the natural log of K is equal to something, there's one part which is temperature dependent. That's actually the enthalpy part. It's the negative of the standard reaction enthalpy divided by the gas constant times the temperature. That's the temperature dependent part. And then there's a constant term, delta S over R. So the equilibrium constant has two parts, one that's changing with temperature and one that doesn't, and the temperature dependence is related to the enthalpy part. So the temperature dependence of K depends on the standard enthalpy for the reaction. So what's the end result? The end result is that if the reaction is endothermic, if the temperature increases, then K increases. And it's not a small temperature dependence. You remember that was the natural log dependent upon this, so it's increasing exponentially. So it's a big, big, big change. this is one big misconception people have. People often think endothermic reactions don't happen unless you raise the temperature, and that's not true. They can happen spontaneously all the time. They happen more as you increase the temperature because you're making the equilibrium constant larger and you're shifting the equilibrium farther to the product side. The opposite happens for endothermic reactions. Endothermic reactions, as you increase the temperature, then the equilibrium constant gets smaller and the reaction is going to shift back towards the reactants. We can plot this up graphically looking at the previous expression that we had, where we had the natural log of K plotted versus 1 over temperature, and that actually makes a straight line. So 1 over temperature is hard to think about. On the left-hand side of the equation there, all the way at the axes, that's where the temperature is infinity. And then as we go to the right, the temperatures are getting lower and lower. And so here I've shown two possibilities where delta S is the same for both of these reactions. And delta S is actually what the natural log of K would be if the temperature was infinity. The natural log of K would then just be delta S divided by R. And then as we move to realistic temperatures, away from temperature equals infinity, we see either that K gets larger as we go higher and higher, that's the exothermic reaction, or it gets lower, and that's the endothermic reaction. And this is very useful to realize because this is another approach we use in chemistry. It's actually a different way to measure delta H instead of calorimetry. There are lots of reactions where the heats are so small because there's so little material, it's difficult to actually measure a temperature change. But we might be able to measure concentrations. And if we can measure concentrations, we can probably calculate K. And if we can calculate K, we can calculate the natural log of K, and then we can make a graph, the natural log of K versus 1 over temperature, and we can measure the slope of that plot and extract from it both delta H and delta S, because the slope is going to be minus delta H over R, and the intercept is going to be delta S over R. The so-called Van't-Hoff plot, and it is used a lot in chemistry and in particular biochemistry to measure very small heats of reaction.